SwayamPrabha. Digital India. Educated India.
Good morning, friends. In the last experiment we had on cruise climb, right? Okay. So how was the experiment? Could you get the data? How many of you felt sick? Some vomiting tendency and all? None? Sure? So what was the speed at which you were cruising? How much? 100 knots. Okay, 100 knots around that. What is the takeoff speed for this airplane? Anybody has noted? 70 to 80 knots. That is roughly 40 meters per second. Okay, that's good observation. So yesterday, whatever briefing we had on cruise climb, that was primarily to check what is the drag polar of the airplane. And essentially, we tried to find out CD naught and K, right? And also from rate of climb experiment, we tried to find out what is the speed at which rate of climb is maximum, right? What was the basic assumption on those theories when you wrote the expression for rate of climb or for a cruise? It's a thrust equal to drag, lift equal to weight. What is the basic assumption? Assumption was the aircraft is statically stable, dynamically stable. Otherwise, we cannot write those equations, right? So what is the meaning of static stability? When I say an aircraft is statically stable, what is the meaning? What do you understand by that? So let us first see that, okay? What is the meaning of static stability? Just I'll go through quickly because these things are already available. When you talk about static stability, we mean the aircraft in equilibrium, if it is disturbed by some external agency or internal agency, and once the disturbance is withdrawn, if it has an initial tendency to come back to the equilibrium, we say statically stable. The catchword is initial tendency to come back to equilibrium, right? And what is the meaning of dynamic stability? It should not only have initial tendency, but in finite time, it should come to the equilibrium. So in dynamic stability, we are talking in terms of time response, right? In static stability, it is only the initial tendency. That should be very, very clear, right? And if you recall in your stability and control course, we always use this sort of a graph, say Cm versus alpha, right? The slope should be, for static stability, this slope should be negative, right? How we appreciate this? Let us say this point, we will call it a trim point. Trim point means at this point, net Cm is 0. That means all the moments because of engine, because of aerodynamic forces, all net summation is 0 about the center of gravity, correct? So this is the trim point. And now I want to check whether the aircraft is statically stable or not. How do I check? I say, suppose for some reason alpha has increased because of, let's say, upward gust has come, right? So the moment this upward gust comes here, what the airplane does? Airplane generates a negative moment when the angle of attack is increased. So negative moment, it will try to have an initial tendency to give nose down moment. So initial tendency to come back to the equilibrium. Similarly, for a situation where suppose alpha gets reduced because of some disturbances. So what this will do? The moment alpha is reduced from this graph, you could see it will generate a positive Cm, right? Which will try to take the nose up. That is initial tendency to take it back to the equilibrium. So once the Cm versus alpha, or we say dCm by dCl or dCm by d alpha is less than 0, we say the airplane is statically stable. No issues? Now, to extend it further, we know if dCm by d alpha is less than 0, it equivalently means dCm by dCl is less than 0. This is obvious because, dCm by dCl I can write as dCm by d alpha into 1 by dCl by d alpha. That is dCm by dCl, I can write as dCm by d alpha into 1 by dCl by d alpha. Right? In a linear understanding, if everything is linear, I am very happy. Those two things are equal mathematically. And since you know for static stability, this man has to be negative. And what is the sign of dCl by d alpha? Cl alpha is always positive. So if dCm by d alpha is less than 0, it automatically means dCm by dCl is also less than 0. So for static stability, we can also say that it is equivalent to state dCm by dCl less than 0. Right? Clear? Now let us go one step deep into it. If I take a wing, let us say a wing is here, and let us say CG is somewhere here, and if I want to ensure that this wing is also in flight, it also is statically stable, then where do I put the aerodynamic center? Where the aerodynamic center should be vis-a-vis the CG? Will the aerodynamic center be behind CG or ahead of CG? Behind CG, right? Or if I put indirectly, because I know aerodynamic center of a wing, which is based on an aerofoil cross section, is for a low speed is almost fixed at a quarter chord point. So my statement should be corrected saying that where do I put the CG to ensure that aircraft is, which is a wing, is statically stable? The answer would be make sure the CG is ahead of the aerodynamic center of the wing, right? So CG should be ahead of aerodynamic center of the wing. Let's say this is the aerodynamic center. You all know what is aerodynamic center, right? Now let us check whether it follows this trend Cm versus alpha, the slope should be negative. Okay? We want to check that. So what we can see here, if I give a disturbance delta alpha in flight, what it will happen? It will lead to a lift force delta L, which I am drawing perpendicular because the alpha is small. Ideally, this lift should be perpendicular to velocity vector, but since the angle is small, I am taking liberty to draw it like this. So the moment because of delta alpha, there is a delta L. Since AC is behind CG, now we see that delta L is acting behind CG, which will give a nose down moment. So dCm by d alpha is less than 0. So it is statically stable. This concept we all know and it's clear now, right? If I look for an aircraft, you see that there are components like horizontal tail, wing, then you have fuselage, there is the engine, right? All will contribute towards the pitching moment. For example, if you see wing, whatever forces acting on the wing, depending upon where is wing aerodynamic center, whether it is behind CG of the airplane or not, that will decide sign of the pitching moment because of wing. Tail, aft tail, you know it will be invariably behind the center of gravity of the airplane. So you know aft tail will always give a negative pitching moment for a positive angle of attack. From the thrust point of view, if you see ideally thrust is like this, but if there is an angle of attack, that means the air, it is pushing the air like this. So there will be a normal component of thrust also here, we denote by NP. This part is clear? So this will give a positive Cm about Cg, right? So if I recapitulate, if engine is at the nose, this will always give destabilizing effect because for a positive alpha, I want negative moment. But engine, if it is like this, for a positive alpha, it will give a positive moment. So this will be destabilizing, right? Wing, depending upon whether the AC of the wing is ahead of CG or behind CG, it will decide whether it is stabilizing or destabilizing. But one thing is for granted that the tail will always give stabilizing contribution, right? So for the whole airplane, equivalent to an aerodynamic center, we define something called neutral point. Okay, we call neutral point. And how do I define neutral point? Let us understand that. See, if it was just a wing with aerofoil, nothing like a fuselage or a tail, then if this is the aerodynamic center of the wing, which you know for a low speed, it will be at quarter chord point, right, C by 4. So this is the AC. Now I start putting CG here. So will the aircraft be stable, statically stable or not? Stable. Now I push it backward. I put it here, CG. Then aircraft stable or not? Statically stable. If I put this CG here, exactly on the AC line, statically stable or not? Neutrally stable. Very good. And if the CG comes here, then it will be unstable. So now allow me to define neutral point. Neutral point is that CG location at which the aircraft becomes neutrally stable, right? Or stability becomes neutral. So for a wing type configuration, what is the neutral point? It is aerodynamic center. Now for an airplane like this, the neutral point will be decided by how effective is the horizontal tail, because this is giving stabilizing. So for an aircraft, we have got a certain point, depending upon the size and aerodynamics of whatever surface you are using, there is a CG location at which the dCm by dCl or dCm by d alpha of the airplane will become 0. So that is the neutral point. That is, if the CG is put behind the neutral point, the aircraft will become statically unstable. Is this part clear or not? You all have done this, right? Okay. Now we have to do an experiment by flying an airplane. So we have to do an experiment by flying an airplane, and using the data we want to find out what is the neutral point of the airplane. Definitely we are not going to fly with a configuration where CG and neutral point are coincident. We will not fly at a neutral stable conditions. We will be flying in a stable condition, but from data through extrapolation we will try to find out what is the neutral point. Is this clear? Right? How do I do that? If you recall, you have, just I will write this, this is also if you recall from your stability and control course, if I want to find out how much delta E required to trim an aircraft at a particular CL for a given CG location, so I can easily find out, suppose if I trim at this point at this CL, what is the delta E required will be given by this, right? Which is expressed approximately like this, right? Could you recall this? Okay. Now, what is dCm by dCl here? Is the static margin, right? So, and now we could see that if I am interested to find what is that CG location at which dCm by dCl equal to 0, how do I conduct that experiment? That is the question. There is a very innovative way of thinking into this is dCm by dCl I can write as dCm by d delta E into d delta E if I assume everything trim. If I assume things to be linear, then I can always write it like this through a chain rule, right? So we are talking about neutral point N naught. Let's say bar. When I say bar means it is non-dimensionalized with mean aerodynamic chord of the airplane. So if you want to look for N naught, that is the CG location, I say XCG bar, for which dCm by dCl is 0. So equivalently I can say from this expression that dCm by dCl is dCm by d delta E into d delta E by dCl trim. What is dCm by d delta E? Control power, so that cannot be 0. So it means If dCm by dCl is 0, it equivalently says that d delta E by dCl trim is 0. Correct? Is it okay? Now the point is, when I am doing experiment, if I want to find out that CG location, what measurement I need to have? I need to measure what is the elevator deflection when I am trimming the airplane, and what is the CL trim. CL trim, how will you find out? CL trim I will find out from lift equal to weight. Lift equal to weight at trim. So let's say at this point, lift is equal to weight. So I know CL will be equal to 2 W by S rho V square. And all these things you know how to measure. Rho you know how to measure through, how to estimate through temperature and standard table. And V you know from airspeed indicator, and you can always do corrections. So these things are known to you. So CL trim you know. Only thing, for that CL trim, what is the delta E required that you have to measure, right? And to just give a better understanding for this, you can use this graph for understanding. Suppose you are, let's say this way, I will explain differently. Suppose I am flying such that Cm versus Cl graph is like this. You all agree that dCm by dCl has to be negative. It has a negative. So trim point is here. Suppose you are flying at a CL trim 1. CL trim 1 means you are flying at a velocity v and density such that lift equal to weight for a given weight, right? Now you want to fly at this CL. So your stability will not change. Then what you have to do to fly at this CL? The moment you want to fly at this CL, this airplane will do what? It will generate negative pitching moment. It will say, no, 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 I will not allow you because it is statically stable. But you have to hold it. So how do you hold it? If it is generating a negative pitching moment, you have to generate a positive pitching moment. How do you do that? By putting elevator up. So that is the elevator we are talking about. Right? Okay. So you have to, this will be corresponding to the elevator up. And as long as you can measure how much the elevator has been deflected, as long as you estimate CL, I am happy. 2 measurements are made. So that is what is required. So before we go to the next, how to process this, let us briefly discuss how do you measure elevator deflection. Okay? Then we will come back to this. See, after all, this is your aileron, sorry, or aileron, elevator, whatever it is, control surfaces. Deflection means it goes like this, or it may go like this, right? Going like this. So what do we do? At this point, we attach a rotary potentiometer. You understand what is rotary potentiometer? All those knobs, etc., when by rotation, the resistance will change, the voltage will change, right? So we put a rotary potentiometer here. So as the pilot give a deflection, there is rotation in the arm of the rotary potentiometer, so that will give a different voltage, and that is recorded through a lab view, whatever setup we have got, which exposure you will have separately. And if you calibrate that, this much voltage means this much deflection. So on the laptop you will find automatically it gets recorded. Okay, you have to only do some sort of initial tapping here and there. But the physics is we use a rotary potentiometer which is linked to the movement of this control surface. As it rotates, the potentiometer shaft also rotates. As it rotates, the resistance changes, the voltage changes, and from the calibration, we find it is equivalent to 2 degree, 3 degree, or 4 degree. Right? So this measurement is done. So once we are confident about this, let us see how to build our theory for this. So we are talking first about neutral point. Generally we say stick fixed. So what we have seen, neutral point stick fixed is that CG location at which dCm by dCl is 0, which is equivalently, I say, neutral point stick fixed is that CG location at which d delta E by dCl trim is 0. Correct? So what I will do? I will go again, as I told you, go and note down what is the altitude and what is the outside air temperature. This you must note down. Now the pilot will be setting his airplane in trim. That means he will be doing cruise. Okay? So he will be doing a cruise at speed V1, and you note down through your laptop arrangement what is the delta E for that configuration. Right? Suppose you are cruising at 60 knots, delta E will be recorded on the laptop, say 2 degree or 3 degree plus. So that you are noting down. Similarly, he will again cruise at V2, delta E2, V3, delta E3, like that. So you will have, for a particular configuration, the value of V1, delta E1, V2, delta E2, V3, delta E3, like different combination. So what you will do, as you have done this experiment, you have noted down what is the speed and what is the, and you know very well, I am trying to find out what is the XCG location for which d delta E by dCl trim is 0. So one is delta E and CL trim. CL trim, you know how to find out. Delta E you are measuring. You have to measure XCG also. So what is the solution? Before you go for experiment, you take the airplane, we will be using Hansa 3, take the airplane to the balance, and pilot will be there. Either he will be sitting or a person who has the equivalent weight of, he will be sitting, and the person who will be doing the experiment will be sitting in the co-pilot seat. Then the other friends will take the reaction, so that offline you can find out what was the CG configuration you are flying. Is it clear? So if different students are sitting in a different flight, the CG will change. CG will also change because fuel will be different. So you are generating the data for different CG location. Is it clear? So you are generating data, that is data means for this speed or for this CL, what is the elevator deflection required? You are generating for different CG location means different static margin values. Clear? Okay. So you have delta E and CL trim. Let us say this is some point here. Or let us say delta. You may get value something like this. Say 5 point you have taken. And this is for XCG1. That is, one group has done this experiment. That one group, one member from the group will be flying with Hansa. Now the next group does the same thing. He again takes what is the altitude, what is the outside air temperature, what is the speed, what is delta E for different speed domain. He will note it down through laptop arrangement. So he does that, and then he generates number something like this. So this corresponds to XCG2 location. Then another party who does something like this, maybe it is XCG3, like this XCG4, XCG5 combination. Now, what is your aim? Your aim is to find neutral point. So how do I use this data to find neutral point of the airplane? That is the question, right? So now let us see, if I use this graph, from each CG location, I can plot d delta E by dCl trim versus XCG location. Isn't it? You see, you take this XCG1, take the slope of this line, that becomes d delta E by dCl trim, and this corresponds to this XCG1. So I take that value, and let's say this corresponds to this. Similarly, for another is this, another is this. Now I join them, and wherever it cuts, what is this point? This is the XCG location where d delta E by dCl trim is 0, and that is our neutral point. You find neutral point by this method. Okay? Clear? Everybody is clear? Theory analysis. So what you have to do when you go for a flight, once the pilot starts trimming, note down the altitude or also temperature, speed and delta E. Delta E will be recorded in the laptop. One of our RA will tell you how to use that. And then offline you will be processed like this. So now after this neutral point is over, he may do something on maneuvering point. You remember what is the maneuvering point? Suppose the airplane is statically stable, and when it go for a maneuver, will it become more stable or less stable? See, as it moves like this, then the tail plane will see a vertical component of air. So that will increase the angle of attack tail. So that will give a nose down moment. So it will give a more nose down moment. So if more nose down moment is there, it amounts to stability being more, right? So that is why, also in your dynamics course, that this has something to do with damping of the system, no? CMQ comes. So in general, if the airplane is maneuvering like this, because it's the aft tail, as it moves like this, the relative air comes like this, that gives an additional angle of attack, which gives a nose down moment, which helps in making it more stable. So the aircraft can become more stiff. So we have to find out what is the CG location. I can correlate that with maneuvering point. We call it maneuvering point. We do not call it a neutral point. Correct? So and by definition, if you recall your flight dynamics or flight mechanics lecture on stability and control, the maneuvering point NM, non-dimensionalized with mean aerodynamic chord, is defined as that CG location for which d delta E by dn equal to 0, where n is the load factor. Am I correct? And how do you define load factor? L by W, which is nothing but 1 by cos phi if it is a turning flight. If you are turning like this, the load factor becomes 1 by cos phi. Is it clear to everybody? Okay. So now we will be doing this experiment using a steady coordinated turn or turning flight to find out the maneuvering point for this airplane, which is Hansa 3. So what I have to do? I will again, the moment this first experiment is over, pilot will tell now I will go for a turn. So note down what is the altitude, what is the outside air temperature, right? Then note down what is the V. You will say I have started turning. You are supposed to carry a stopwatch or a mobile phone. You should also see if he is taking a 90-degree turn, how much time it is taking, so that you can get a rough idea of turn rate. Please note these things, right? That will not be recorded in the laptop. Now what we do, as he is making a turn, he will be banking. How will he make a turn? He is going like, because it's a turning flight. It goes like this, banks. And this lift component will be used for turning. So at the same time, the important thing is, you have to adjust the angle of attack such that by banking it should not sink. It's a coordinated turn. It cannot lose the altitude. So it's very important, you need to note what is the V at which he is turning. It will be done by only one person, because there is one person who will take the reading in Hansa. And then you note down what is the bank angle, right? And then also note down what is the time taken for making the turn. You may say I will take a turn, 90-degree turn. So check the turn bank indicator, 90 is over, stop it. Okay, these readings you have to take at least 4 or 5, whatever he will be giving. Then offline you will be processing. Is this part clear? Also, this delta E will automatically go, other parameter will automatically go into the laptop. So don't worry about it. As far as you are concerned, V will note down. You will note down what is the bank angle and delta T. Rest will automatically go, you have to press some button. So once you know this, and once I understand, maneuvering point means that CG location for which delta d delta E by dn equal to 0, I should now understand how do I process the data before I go for experiment. Understanding must be there so that you can conduct the experiment correctly. So what you will have? You will have, again you have a CG location because you have already noted down your weight. So delta E and n you can plot for different speed and different bank, or he may sometime make a turn at the same speed, right? So that part you have to check. So you plot delta E versus n. This is for a XCG1 location by one group, one member of the group. Second, again he does the other group does the same thing, and this is corresponding to XCG2. There could be another group with XCG3. So there will be 7 groups, I suppose. There are 30 students, means around 7, 8 will be there. So once this data is collectively plotted, now you have to do what? You simply plot d delta E by dn, and here XCG. Now you plot take the first graph xcg1, see what is the slope here. The slope is d delta E by dn corresponding to xcg1. Is it clear? So you write here xcg1, and this is the point, first point, second point, third point, fourth point, and then join them, extrapolate. What is this point? This is the xcg location at which d delta E by dn is 0. So this is your maneuvering point. Is this part clear? Right? So once you do the exercise, once we take the data and process it, then you will get better feel for this. But please understand, when you are doing an experiment, things are not so smooth, right? You don't expect all the points will be in a straight line. There will be measurement error, there will be modeling error. So that is why in practice we do many experiments and take the best fit, so that we try to minimize the noise or inaccuracies. Okay, but this is a part of exposure to this course, so you should know how it is to be done. Okay? And be sure that when you fly with the Hansa 3, you have seen all those instruments, where is the outside air temperature, which one is the airspeed indicator, which one gives you turn bank indicator, etc., so that you don't lose time on that. Right? Thank you very much.